carries on for the next 10 minutes. Play man. Well, nice good turnout tonight. So good to see you all, despite the cold weather. A couple of things before we start. Jim will be doing his kind notes. You want to do them after the tea or before the tea?
Well, if I could do them before the tea, if it's possible, it depends.
Yeah, we'll try and do them before the tea. So we'll get sky notes for the next month of things floating in the sky. So the other thing is, we're getting close to having our own observatory, the Hatton Institute Observatory, up and running. There's a few things still to do, but we're hoping to open it in the near future, or moderate in the near future. What we want to know is how many people are interested in using it. How many people? Andy? Yes? Yeah? Okay? Cody? Yeah? Right. Pam maybe? June? Yeah? Okay, well that's good. Yeah. Right, it's good to see that. I'll send out an email asking for feedback from the people who aren't here tonight. But yeah, it'd be good to actually have it up and running and get people in there and using it, because that's what it's all about.
Just in time for the summer.
Yeah. So you can observe the sun. The moon's always there. You can see the moon. Right, so tonight's talk we have... No, okay, come to that later. There will be an additional charge for those wanting to use the observatory because we have to pay for its upkeep and maintenance, but it's not big. So if you can afford the DAS fees, you can afford the observatory fees.
You get the mechanism out on these old seaside telescopes.
That's great. Pound coins in, you get 10 minutes for a pound coin. No idea, Michael, but I shall implement that. Right, so anyway, tonight's speaker, Colin. Steele has a long association with Dundee Astronomical Society. I'm told he's first joined the society in 1978 as a young lad. He used to get a lift up to the observatory, and in those days it was very much a different style of DAS from what we have now. It was like stay all hours of the night at the observatory, doing TLP observations for Patrick and so on.
I don't remember it. I don't remember it.
Oh yes, and he is now an honorary member, of course, one of our honorary members, and he's now working at Manchester University in the mathematics department, primarily teaching mathematics, but still a strong interest in solar physics, which he does a little bit of now and again. And tonight he's not talking about solar physics, he's talking about Saturn, so I'll hand over to Colin Steele for a talk, Horseshoes on Saturn. Do you want the lights out, other one?
Yes, fairly low if possible.
It's either
Alright. Well,
we don't have any of those fancy...
Yes, this is fine, yes. Well, firstly, thanks for coming along. I was going to say thanks for inviting me, but in a sense I kind of bullied myself into I saw there's a space on the programme, and kind of decided, well, this is as good a chance as any. It's been a long time since I've given a talk here. I did, of course, come up for the 50th and the 60th anniversary meetings for the Society, which did have elements here, but as for giving a talk, well, this is, I think the last one I did come back shortly after I first left, and I think I came back around 95, 96, and well, this is the...
Went out for beer. Went out for beer.
I'm sure we did. I can't quite remember, but I'm sure that we did. So, I mean, I've turned into a bit of a nostalgia about things, and one thing that's I haven't had too much beer just now, but I wasn't expecting to be pointing over in this direction and pointing at the door here, because of course it used to be all this way round. There's been a right angle turn in the society, but as has been mentioned, later this year it will be 40 years since I first came through the door there and came to one of the meetings, and over the times that I've been involved, every little era has been that bit different from each other, but it's all been very enjoyable, and of course I'm aware I'm missing out on quite a lot these days. But, I mean, looking back to those early days, I think it's with apologies to some of the committee members at the time. It was probably when I first joined. There were maybe 4 main figures in the society. Now, when I first joined, Ken was chairman, and what I remember after that first meeting, he came over and he spoke to me, and I was, here was me, I'd just come up, and then now the chairman was speaking to me. And I think, that's a great thing for societies to do, to make sure that that new members are welcome.
You thought chairmen were important people in those days?
And it was a few years later that I found out otherwise, yes. At that point, treasurer was Dave Taylor, and he became chairman not long afterwards, and I served as various officers, took various offices in the society. They've taught me a lot about the workings of committees and so on. Secretary, when I first arrived, this was Tom Flood, and yes, I learnt a great deal from him. Of course, sadly, Tom, who's no longer with us since the late 80s, and sadly, to add to this list, there would be other people that I interacted with very positively in the society: Sandy Mackenzie, Cathy Jenkins, Ed Lynch, and more recently George Prophet. Obviously, with each announcement that I've heard there, it is a sad event, but of course, with all of those people, there have been very positive things in their times. The 4th figure from the early days, and in many ways, except one, the biggest name of them all, was of course Harry Ford. Harry really ran the show. There was maybe less distinction between the society and the observatory those days, as opposed to now, but his infectious enthusiasm rubbed off very positively on the society, and in a sense I did regard it as the end of phase 1 when he moved down south to take up positions at Southend and then at Greenwich. Of course, if I say there were 4 figures, there was one other figure who didn't come that often because he lived in places like Fort Augustus and later in Edinburgh. I refer, of course, to Dave Gavin, who within a year or 2 of me joining had actually become honorary president, so he was very much part of the situation, although not along so often. Well, I don't want to give a history of everything that's happened here, although I can't help mentioning, now that we were talking about doors, I take it we still do have the other door here, because of course one thing I remember is when I would come into the early meetings, I'd sit down there, and then it was almost as if the meeting was about to start, the committee would march in one by one through this door, having a meeting to just decide the night's events, and that was just a little ritual that I remember from those days.
Could start doing something.
Now, probably a few things in the way at the moment, but during those early days, I went to many, many interesting talks. Possibly there were 1 or 2 talks that I would say were slightly less interesting than the others, but not many. But, of course, yes, I knew that there would be a time I would want to give a talk. And, yes, I told myself it would be nice to give a talk on the moons of Saturn. Now, when I did give a talk, I'm not quite sure why, I moved slightly away from that topic and gave a talk about discoveries of moons of the planets. I'm not quite sure why I moved away from the possibility of giving a talk on the moons of Saturn, and shortly after that I started giving more and more talks on meteors. This was in the days that rather than having the computer projector, we would use, there was a slide projector up here, or we had an overhead, and I remember on one or two occasions Mike would ask me, what happened to that green acetate about meteors? It still exists.
That's the original.
But
I'm waiting for the famous photograph with the lamppost and the deck chair.
oh, right. I don't have that one with me tonight, but
Oh, curses.
I'll see if I can find. Yes, let's see what I can do there. But I didn't actually give a talk on the moons of Saturn. But now I have an opportunity. It's not quite the same talk that I would have given then, and we'll see why. But I've entitled this one Horseshoes on Saturn. Although it will take a little bit of time to get to the horseshoe. So, if you were to go out and ask some members of the general public to draw a planet, what would they draw? Now, I took a fairly small sample, as in 2.
For your children.
That's the one, or the 2. And those are the 2 that they drew.
Brilliant.
Now, we see something that those 2 both have in common. Okay, we've got the prolateness here rather than the oblateness here. But the obvious thing is they both have rings. This one even has a division in the rings. We've got a couple of great red spots or great white spots, transfers from Jupiter or Neptune here. But there is something about Saturn. And we were discussing this before we came up here about, yes, it must have been even earlier, about 1972, that I came up to the observatory with my parents, and the image that really stuck with me over the decades was just seeing Saturn through the telescope upstairs, and that's something that's the delicateness of all the detail that you could see there, that's something that stayed with me for a long time. So there is something about Saturn. Well, what do we know about Saturn? It's a planet that moves around the ecliptic. Over the course of a year, it makes a little backwards and forwards movement, which is effectively a reflection of what the Earth is doing, but over a period of 29 to 30 years it makes its way once around, well, near to the ecliptic here. So you can see each year it just zigzags that little bit further along here. So we go through periods where Saturn is easily observable, we go through periods where it's less well observable. Possibly at the moment, but good times will come again. The ancient people clearly knew about Saturn. Saturn was one of their 5 or perhaps 7 planets. What the ancients, and of course I'm generalizing here when I say the ancients, there were many civilizations in different parts of the world that independently categorized those 7 objects as being that bit special, but it does seem that most of them regarded, yes, the sun and the moon and 5 other objects as being special, wanderers, planetos in the various languages, brighter than all but the very brightest of stars, performing motions in the sky. Okay, Saturn's one was every 12.5 months, going around the ecliptic once every 30 years. The ancient people knew a lot about Saturn, so when the telescope was invented, that Saturn was an obvious target for people like Galileo or various contemporaries, and well, actually, Galileo couldn't quite work out what the deal was with Saturn. He did a few different drawings of it that, well, when we look at something like this, we think it couldn't be far away. Sometimes they seem to see 3 different objects next to each other. there were times, it's not recorded here, he would just have, a simple disk and no difference to it. So Galileo was a bit puzzled by Saturn, and it took observations later on in that century by Huygens to work out that yes, the reason Saturn kept showing different kinds of appearances was it had this ring around it, this series of rings, and we were seeing from different angles. So sometimes, yes, we would see wide open rings, at other times we would just see the planet without the rings. Huygens also discovered the first of the moons of Saturn. He discovered Titan around 1655. More moons followed, 4 at around the same time. Cassini, a name that we'll hear a little bit more of later, Iapetus, Rhea, and then slightly later Dione and Tethys. But he also discovered the division in the ring system. So, several rings. By now we've got 5 moons. More were discovered. This gentleman gets into virtually every story involving astronomy, and no doubt various involving music and so on. Discovered a couple of the inner moons, Mimas and Enceladus, and then in the 19th century, Hyperion, Phoebe were discovered. First photographic discovery of Phoebe, and then, yes, I remember at various points in the 1970s wandering into Broughty Ferry Library and having a look and seeing Saturn has 9 moons. Here are the names, and there was very little else that they had to say. They could give a table of a few things, but that was the situation according to the books which were in the libraries around the mid-70s. I give slightly complicated wording there because, of course, the books were not necessarily new at that time, and one other development had started to happen. In 1966, the Earth passed through the plane of the rings of Saturn, so the rings were edge on, and this allowed a 10th moon, a 10th satellite, to be discovered. There was always something just that little bit funny about this 10th satellite. Some of the observations didn't quite match up. There were a few issues with the orbital period. So, yes, some of the books in the 70s, the newer ones, would say that Saturn has 10 moons, but sometimes in a slightly apologetic manner. But everything changed. When Voyager went to Saturn, Voyager 1 having been to Jupiter, Voyager 2 also having been to Jupiter, and then going out to Uranus and Neptune, there were many discoveries made. More parts to the rings, strange spikes and spokes, but as far as this 10th moon, which had been called Janus, it turned out, well, there were actually 2 of them, Janus and Epimetheus. So we were up to 11 moons, and then when Cassini visited, starting off from 2004, and indeed the story has only just ended in a very spectacular manner, many, many more discoveries. Saturn has a lot of moons. Well, looking at Saturn itself, we can see a bit of data here. The 6th planet, this isn't quite to scale, but you can see there's Jupiter and the inner planets closer to the Sun, Uranus, Neptune, and yes, let's keep Pluto here. It goes slightly in and out as it goes around the Sun, but Saturn itself, it's the 2nd biggest planet in the solar system. If we were to look at the Earth and Saturn together, you can see just how much bigger Saturn is than the Earth. But we also see that if we were to start a circle at the south pole of Saturn, the Earth would just poke out of that circle at the north. The difference between the equatorial and the polar diameters of Saturn is just that little fraction too small for the Earth to fit in. So there's a large flattening, and that is, of course, because Saturn actually rotates around very quickly. So Saturn, you can see, it is almost, in size, it is almost as big as Jupiter, and then considerably bigger than Uranus, Neptune, and any of the inner planets. But although Jupiter is only just that little bit bigger in a linear sense than Saturn, Jupiter weighs as much as almost 3.5 Saturns. So if we could get some kind of a bizarre experiment involving weighing scales, it would take 3 and a bit Saturns to balance Jupiter. So, what do we conclude? Saturn is big, but it's not particularly heavy. It turns out it's the least dense of the planets, and in another bizarre experiment, if we were to find a piece of water, a stretch of water large enough, Saturn would float. Now that's an experiment I would like to see carried out. There would be a few practical difficulties, but let's not let those ruin things for us. So, Saturn itself. You can see it does have various belts and bands. It has an aurora, and there sometimes are magnetic fields. The occasional spot, perhaps it's repeating at certain parts of Saturn's orbit. Strange features like the polar hexagon here. So there's a lot going on Saturn. Perhaps it was a little bit unfortunate for the globe of Saturn itself that, yes, Voyager came having been to Jupiter, so there were bound to be comparisons there. But even if Saturn's globe lost out in comparison to that of Jupiter, the fact that you've got the rings, Jupiter has rings, but Saturn has real rings. Look at them here. Now, the exercise is to count them. No. It used to be thought that, yes, there was an A ring here, a B ring here, a C ring here, but we look at the number of them, there's hundreds of them. Yes, obviously you can catalogue them, but it's not the kind of solid type object that was perhaps once thought. Okay, we can always go to town on the artist's impression and see various objects there, but it's a complex system of threads and gaps. And look at this. We get some features within the rings. Features that actually rotate as the rings move round. Under simple celestial dynamics, you would expect if any feature was there, it would fairly quickly get distorted away as the inner part rotated that bit more quickly than the outer part. So, mysteries there. As mentioned, Saturn opens and closes the rings. Well, Saturn's always pointing the rings in the same direction, but we move around, so there are times that we will see the southern parts of the rings, times that we'll see the northern parts of the rings, and times where we will actually, around 2009, that the rings will be edge on, so there's not, we won't see much of the rings. That, of course, is a disadvantage if you want to see the rings, but if you want to study the area near the rings, having the rings as faint as possible can be an advantage. Yes, the pre-Voyager thoughts A, B and C, and now, well, A, B, C, D, F, various rings on the go, but it's not as if a ring is a single object. There are many sub-rings within them as well. Just for comparison, if we were to imagine here, well, if we were to have the Earth in blue here, Saturn in yellow, the A to C rings in this reddish orange, they would go out to almost halfway out to the Moon's orbit. That gives an impression of the size of the ring system on Saturn. But, I've set the scene, let's now look at the moons of Saturn. The Earth has one moon. Other planets have more, except Mercury and Venus, they don't have any. Mars has two. And there was a time that, yes, I thought it was an injustice that this relatively big thing like the Earth had one moon, and this smaller planet actually had two. But of course you could say, well actually, compare our moon with the moons of Mars, and there's no real comparison there. But Jupiter and Saturn have many more moons. Saturn, we're talking about 61 or 62. Now, the catalogues were fairly clear on 62, but more recently there's at least one object they're having their doubts about. Not so much whether it exists, but whether they need to draw a line somewhere about what is a moon and what is just a large bit of rock. But there's lots of ones that they are considering. The problem is that they get the data comes in, when there happens to be Cassini or another space probe there, so it's a little bit difficult to just say we need more data and then get it. Tends to come more in bunches there, but we're up to about 62 moons of Saturn. 53 of them have names, and yes, we will see various of the names here. Now, I'm not going to bore you with minor details of graphs and so on. Well, maybe not too much. But if we were to plot how far out the moons are along the bottom, and then how big the moons are up the side, we get an interesting pattern. Now, I hasten to add, this is not the horseshoe. We'll come to the horseshoe later. For those who are interested, you will see I have plotted things logarithmically, which is a way of being able to compare quantities which are one very large and one very small without it seeming a bit ridiculous. You can keep some of what's actually going on there. So we see, yes, I don't know if anyone's counted, this might be a bit difficult to count here, but this would be the 62 moons of Saturn. What can we say about those 62? Well, probably one thing we'll say is they fall into certain groups. And one group that I'd like to have a look at are the ones here. I've just blown this one up a little bit more here. I'm not sure if this adds a great deal, but we can call those retrograde outer moons. What do I mean by that? What I mean is those are moons which go around Saturn the wrong way. Go above, well above the North Pole of the Sun, and you will see all the planets move around anti-clockwise. Go above the South Pole of the Sun, the planets will appear to move clockwise. Go above the North Pole of Saturn, many of the moons will appear to go anti-clockwise, including all of the larger ones, but you have this group of them here, which go around the wrong way. If you were to go above the North Pole of Saturn, this lot would appear to go around clockwise. So, I'll be giving a quiz on some of those names at the end. Some of them, they haven't quite completed the process, they just have preliminary names. I'm not quite sure why. I mean, if it's 2004 and they are sure it is a moon, I'm not quite sure why it takes 14 years to give it a name, but you know, you can see some of those names, they don't look particularly like names of astronomical objects. There's a lot of astronomical objects to name, so they do involve the names of accounts of various cultures there, so...
There's a lot of Norse there, isn't there?
Well, that's true, that's... Yes, we've got quite a lot of different ones there. Those are the retrograde outer moons. Now, what can I say about a typical retrograde outer moon? Well, we need to be slightly careful. What do we mean by a typical and average outer moon? And I'd like to compare with the situation. Let us imagine that we were to go to the park and observe that there were lots of people out walking their dogs. And let's say that the number of people was equal to the number of dogs. What would be the average, the typical being there? What would be the average number of legs? 3. If the number of people was equal to the number of dogs, the average number of legs would be 3, assuming we hadn't had any nasty accidents or that. But that wouldn't affect things greatly. But it would not be a typical figure at all. You'd have the people with 2 legs, you'd have the dogs with 4 legs, things averaged out at 3, but you could not claim that 3 was in any way typical. So when we average various quantities and say that yes, the average rather than the typical retrograde outer moon, 7 kilometres, about 4 miles across, it would fit, say, between here and Broughty Ferry. A long way out from Saturn, 50 times as far as our moon, and it would take about 3 years to go around Saturn, going around the wrong way. Not particularly circular, varying by almost a factor of 2 here in distance from Saturn, and, okay, going the wrong way, but even then inclined by about 18 degrees. So that is an average outer moon. Whether it's a typical one, that's a different matter. But we've also got the prograde outer moons, the ones I've drawn in blue here. We can see they do appear slightly bigger, marginally further in. Okay, we've got different kinds of names here. At least they have completed the naming process for those prograde outer moons. And we can see, yes, slightly bigger, slightly further in, so they take 2 years on average rather than 3 years to go around Saturn. But they are actually really quite inclined and quite eccentric. So this emphasises a bit more the difference between average and typical here. But certainly the retrograde and the prograde do certainly seem to be different species. Whether there are other different species as well, that's something that's a bit hard to say. Now, moving further, this one here, Phoebe. We're now talking about specific objects rather than various groups of objects discovered a bit over a century ago. We've got a half-decent image from Cassini here. It's a bit bigger, a bit further in than the prograde outer moons, and indeed the retrograde ones. It was one of the first objects to be observed going around the wrong way, one of the first retrograde objects. If we were to look at the retrograde moons here, Phoebe here, I think we can come to the conclusion that Phoebe is not a member of this particular group. It does seem to be an object in its own right. But it is irregular in shape. You can see here, it's not big enough to have got itself into a reasonably circular configuration. It rotates every 10 hours or so. It's about the same time which Saturn takes. So Phoebe here, somewhat different from the far out moons. But then moving a little bit further in, the next one we come to here, one of the biggest moons, you were up near the top here, Iapetus. Now each of those has its own characteristics, and here is Iapetus, and we can say, well, it's a bit dirty on one side. It is much brighter, it has a higher albedo on one side than it does on the other. There have been various suggestions that yes, one hemisphere, the leading hemisphere, could be scooping up various material, leading to a change in colour, and so on. The leading hemisphere, darker. It takes the same time to rotate as it does to revolve once around Saturn, so it ends up pointing always the same face towards Saturn. But, one of the bigger moons here. In fact, prior to Cassini, it was actually thought to be marginally larger still, but it had been revised downwards slightly. Next one in, Hyperion. Now, odd-looking object here. It almost looks like something that you'll find if you go exploring the Barrier Reef or something like that. Some sponge-type characteristics. I suppose in time we'll get various better pictures of it and be able to say a bit more. But it has some very interesting characteristics in its own right. You can see we're now down to something like 3 weeks to go around Saturn. So it was something like 3 years for the outermost moons. We're now down to about 3 weeks here. But it's the rotation of Hyperion which is very strange. It does not seem to be rotating on a single axis. There is a dominant axis, but this dominant axis is itself moving on a quite quick basis, so really the whole thing ends up quite unpredictable there. There's a lot that we have to learn about Hyperion, and in particular its rotation. Further in, the next one, this is the biggest moon, the largest moon of Saturn, Titan. It's not quite the largest moon in the solar system. It probably vies for second place with Callisto in the Jupiter system, with Ganymede being that little bit bigger. But in many ways, Titan is one of the most interesting objects that there is. There have been speculations that, yes, it's known to have an atmosphere. Arctic impressions abound. Speculation about various methane lakes and so on. Whether we'd be able to see Saturn in the sky like this in between the various bits of lightning, well, that's very much speculation there. What we do know, yes, about 3,000 miles across, it has a significant atmosphere. Now, it was a surprise when the atmosphere was first analysed and found to have a lot of nitrogen in it. Methane didn't come as a great surprise, but nitrogen was really nowhere on the radar until it was actually found there. Every 4 orbits that Titan makes, Hyperion makes 3 orbits, so no doubt this feeds in somewhere to the mystery of the rotation of Hyperion. But Titan, as say with the atmosphere, possibilities for life if you drill down far enough, who knows? I wouldn't get too excited about this one, but it's always worth some speculation. Moving in a bit further, Rhea.
Oh, very good, yes.
You can see it's vying with Iapetus for being the second biggest one after Titan. You can see we're getting closer in all the time to Saturn itself. What can we say about Rhea? It takes 4.5 days to go around Saturn. It's an almost circular orbit. There have even been suggestions that there could be rings around Rhea. So every one of those moons is that bit different. So for that reason I will mention 2 of them together. Tethys, and then just to the right of it, Dione here. What can we say about those moons which were discovered by Cassini? They take just under 2 days, just under 3 days to go around, a few hundred miles across in each case. Tethys has a large crater and a canyon system. Dione has a series of cracks, so they all have their differences, but one similarity between Tethys and Dione, they have other moons sharing the same orbit. Both of them do. Here we have Tethys, and then it turns out that 60 degrees ahead of Tethys, we have this one called Telesto. 60 degrees behind, we have this one called Calypso. And Dione has Helen, 60 degrees ahead, Polydeuces, 60 degrees behind. You can do the maths of it, and yes, 60 degrees ahead or behind, that is a stable configuration. It comes mostly when you consider Jupiter orbiting around the Sun, and the fact that you have the Trojan asteroids 60 degrees ahead, well, the Greek Trojans 60 degrees ahead, the Trojans 60 degrees behind, other than the spies which have swapped over, but it's the same situation. Both Tethys and Dione, you can see here in the diagram, we've got the 2 for Tethys here, one bigger than the other for Dione. They are orbiting around Saturn, but 60 degrees ahead or behind the relevant moon there. The 2 that Herschel discovered, Mimas and Enceladus, you can see there's a couple that I'm going to come back to here. We're getting in towards the inner moons here, so we're talking smaller orbits than our own moon, and just under and just over 1 day. So they go around quite quickly. Enceladus is thought to still have some active geology to it. It's thought, yes, there could be various oceans there. We need to find out more. Mimas has a large crater, which named after Herschel. So various, yes, here we see Herschel on Mimas with a central peak, but look at the surface of Enceladus. Now, that's the outer ones and the earlier discoveries. We've got a few of the smaller moons still to look at. The Alkyonides, that's 3 small moons here, among the smallest of all. 2, 3, 4 or 1, 2, 3 miles across. They take almost exactly 1 day to go around. They are further out than Mimas, further in than Enceladus. But the remarkable thing, they're all accompanied by little ring arcs. Not rings going all the way around, but near the moon there is some ring type material there. There are other moons which are in gaps in the rings. Pan, Daphnis, Atlas. Pan within the A ring. Again, Daphnis within the A ring. Atlas between the A and F rings. They would orbit along in the ring here, but sometimes what they end up doing is sorting out the ragged edge to the ring. So this one works out. You can also see the way that the sun is casting shadows of, well, Daphnis itself and also the various ragged parts. But you can see that, yes, there's ragged stuff up to here, past here, but on the other side here, no ragged stuff at all. So you've got some very interesting things going on with the ring gap moons. Okay, this is another picture I can't quite get my head around here. It looks as if the little parts of the image didn't quite fit together here. Ring shepherds. A couple of moons here. Pandora, Prometheus, just inside or just outside the F ring, and those help the F ring to keep its shape. So any particle which might go wandering off, it's a sheepdog type approach, that the gravitational field of those particular moons helps to keep the ring together. Various other even smaller stuff. Now, we're getting on to stuff which is borderline for being called a moon here. How do you differ, how do you discriminate between a large rock and a small moon? But, sometimes it's the effects that they have, being able to just show the shadows here. And a couple of very small objects down here. Aegean and 2009 S1. That's the one that they were actually having their doubts about. But, you can see just a few hundred yards across within the moons, within the ring. So, are we talking large moonlets or small moons, or does it matter? They're there, we can look at them, but it does raise various questions. So, in terms of questions, have we been everywhere here? Clearly we haven't. Where have we not been? Where have we not been here?
The one you're pointing at.
This one? Let's see. That was also a bit of a spoiled here. Where we've not been here, we had been to Hyperion, but Janus and Epimetheus. You'll remember them from earlier. We were talking about a sort of discovery in 1966 and a fuller discovery about 1980. So, what can we say about Janus and Epimetheus? They're near the outer edges of the rings. And you can see, yes, near some of the rings here, Janus is a bit bigger than Epimetheus. The distance from Saturn, very close to each other, as are the orbital periods, 0.6942 or 6945 days. And that has implications. The difference between the orbital sizes is consistent with the actual size of the moons themselves. So that looks interesting. But the orbital periods, they're just 26 seconds apart in about 16 hours. So over the course of about 4 years, one would catch up with the other. So, what's going to happen when one catches up with the other? What actually happens? Well, let's imagine we have Janus and Epimetheus here. They're very small, about 1,000th of a millionth of the mass of Saturn. And when they're far apart, well, gravitationally, they won't feel each other at all. But Kepler's laws, the one on the inner orbit will orbit that little bit more quickly and will gradually, over the course of 4 years, catch up with the outer one. But what happens then? As the inner one catches up with the outer one, they do start to feel the gravitational force of the other. The red one, the outer one, will speed up the green one. The green one will pull back the red one. It slows down, and as it slows, it falls. But this one, the green one, as it moves forward, it rises into a higher orbit, and then they end up effectively having swapped orbits. Now, I remember reading about this around, the early 80s, and I remember thinking, I was always a skeptic about all sorts of things, and I would try say, no, you can't have black holes, it's too sensational or anything like that. But I remember thinking, well, this can't possibly happen. It just looks too convenient. How can this happen? I can see what the effect is, but is it always going to work? Could it ever go wrong? Would it be happening by the right amount? I was skeptical of it even then. But it turns out, yes, we have those interactions here, and in fact, there was such an interaction earlier this month. Because until earlier this month, Janus was on the inner orbit, but now Janus is on the outer orbit, and that will remain the case for just over, about 4 years from now. So it's nothing to do with the Winter Olympics or anything like that, although you'll find that the dates are very close to that. I think that's one correlation that we'll forget about. But we've got this behaviour happening. So, it looks like I've started to talk about something that's very different here, and my journey here. Well, actually, this is wrong. I did this instead. But let's imagine I had done what I was originally planning to do. I just felt this morning, well, firstly I wanted to take someone to Edinburgh, but also wanted to avoid the possibility of there being icy roads in the Peak District. So, I travelled around 300 miles further north. Okay. But did I? Maybe I travelled 300 miles north, plus around 4,000 miles east, with the Earth rotating. By the way, do we have any traffic policemen here? I came into a bit of trouble once at the Derby Society, talking about this kind of thing. The fact that, yes, am I really claiming to have travelled 50,000 miles with the Earth going around the Sun over the course of a day? I'm not quite sure how that one would stand up in court, but I don't want to be the person to try that one. But if we just consider, yes, in space, in the space of the solar system, I travelled considerably more than the 300 miles. And of course we can never say what is stationary. We can ask, is the solar system moving? Well, with respect to what? We can sort of answer that one within the galaxy, but when we try to go to a higher scale there, we end up in a bit of trouble there. But it would seem that there are different ways of measuring things. But it felt like I travelled 300 miles north. And let's just say, in a frame of reference fixed to the rotating Earth, okay, that's a more definite statement, I travelled 300 miles north. But sometimes when you look at things with a different way of measuring, with respect to something that might be moving, then you end up with different results. And then when I started to travel, okay, I didn't move off with too much of an abruptness, but if I had, I would have felt myself go slightly back in the seat. And you might say the next bit is, I've already confessed to being a lie, that when near Glasgow, which I wasn't, when I turned right, something appeared to push me left, and then when I started up Balgay Hill, there were vertical effects there, but there aren't any forces associated with those things. So what's actually going on? Now, let's have a look at a pendulum here. Here we can see a pendulum going back and forward, but it's actually rotating. What is causing this pendulum to rotate, apart from a computer animation? It turns out, when you're dealing with things rotating, it can appear to give new forces. Because let's imagine that, yes, we've got something in a rotating frame, this green spot. Imagine this disk is rotating and the green spot is moving. Well, we can see here the green spot goes up and the disk moves round. Big deal. But let's say, while we were doing this, we moved the camera around with the disk. What would happen? The disk doesn't move, but the spot moves, and it seems to be turning right. Okay, some of the animation came out slightly wrong there, but it would seem it starts off, there's nothing apparently to cause it to move, but it moves and then it turns right. And if you don't believe that this would happen, let's look at this. What seemed to happen here the ball started off about here, the finger was simply removed, but the ball started to move in this direction and then started to turn to the right. Now, you can also see I seem to be a bit short of breath at that point, because it's all filmed on a rotating platform. It was, one of the roundabouts in the children's parks, and yes, if you're going to do this kind of experiment, do try to take a reasonably young child with you. For one thing, they can help with the experiment, and also their presence can probably avoid you being asked any awkward questions about what you're actually doing filming things in a children's park. But we saw here, we had two different things which happened. If we know it's rotating, then we can see, yes, it's going to move outwards. That's actually called an Euler force, and then when it moved to the side, we call that one a Coriolis force. Sometimes the Euler force called a centrifugal force. Now, of course, we're used to memories of the physics teacher shouting, "There is no such thing as a centrifugal force, it's called centripetal force." But if you're working in a rotating frame of reference, you've got the centrifugal force. It seems to cause things to move away from the centre. But you've also got the Coriolis force, which seems to cause things to want to move to the right. So, why do I mention all this when I was just talking about Janus and Epimetheus? Well, now, I don't want to spend a great deal of time on this at all, just to say that I have written down some equations to balance motion, the Coriolis force, the centrifugal force, the gravity from Saturn, and the gravity from the other moon, Janus or Epimetheus, the one that's not being affected over here. So we're looking at some equations which involve those forces. And as far as solving those equations is concerned, let's let the computer do that.
Teacher can't work his computer.
Okay, come on, have a go.
Always used to be the video, wouldn't it?
Here we have Janus and Epimetheus orbiting around Saturn. Now you can see we seem to have an interaction there. We have one on an outer orbit and one on an inner orbit. And we can see it seems the red one is catching up with the green one. They interact, and now the green one moves away. But then green catches up with red, they interact, and then red leads the way once again. So they keep on interacting here. This interaction, which I said, oh, that can't possibly happen this way, but this is solving the equation. It's important to realise this is not a film or a video or anything. It is solving the equations as it goes on. You can see it's not quite as perfect, it's not quite as neat as nature, and there are various reasons for that, involving things that nature doesn't have to deal with, round-off error, and so on. Every time it seems the orbits are slightly different, and then of course they all come to a shuddering halt at the end of the run there. But possibly you thought that when everything was going around so quickly, it was a little bit more difficult to work out what was actually going on there. So instead, I'm going to put it into a rotating frame of reference here. I'm not going to take out the rotation completely, but if I take out most of the rotation here, you can see they're revolving that little bit more slowly, so we can see better. Green catches up with red, they interact, red forges on ahead. So red's forging on, red catches up, they interact, green now moves ahead. And this will happen several times. You can see it's not quite as neat as the real thing, but it's got the gist of it is working out. And I think we'll see a few more interactions here. They interact quite quickly, almost looks as if one is bouncing off the other, but that's not the way it works. It's all to do with attractive gravitational forces here. What's not quite taken into account is that Janus is a little bit larger than Epimetheus. It's actually assuming that the two, for this purpose, have the same mass, but I'll do a third and final run where, well, if I get it right,
That's going to be my question.
if we change the masses here, so we make the second one about a third or a quarter of the mass it had previously, and at the same time I'll wind the rotation down all the way, so it doesn't look as if we've got that much in the way of rotation at all. It looks as if they're moving in different directions, but that's only because the whole thing is moving in a much more, the whole thing is rotating anti-clockwise while this is going on. Now the green one is Janus, the red one is Epimetheus, the green one is the more massive one, and we see that when we wind the rotation out completely, so we're, well, on average completely, we end up here with Epimetheus going on a larger orbit here, Janus on a somewhat smaller orbit. And now we can see that there's one word that I've been avoiding since the beginning of the talk. This is the horseshoe. The orbit of Epimetheus is the horseshoe, while Janus just does a slight back and forwards here. There's a slight trend here that it might just be some cumulated round-off error. Well, I could spend ages just looking at different scenarios there, but let's get back to, well, we don't have a great deal more time, so getting back to finishing things off here, this is the kind of orbit that we have. Epimetheus here, Janus here. It takes 8 years for the whole thing to happen, with 2 interactions on the go. So we have, yes, once every 4 years, including around the time of the original discovery, we have one of those interactions there. Now we can see actually when we compare the various forces on Epimetheus, Saturn has by far the greatest force, then it's the Sun, and only then, well, Titan, some of the other outer moons do. Janus is of a similar amount to Titan, the other planets not very much at all, but it's the fact, the repetitive nature, the fact that Janus is in the set of places that it is, that causes it to be significant. So just to finish, what would we see from Epimetheus? We would look up and we would see Saturn in the sky, 47 degrees across at magnitude -9. We wouldn't need the big telescope upstairs to get the best views of it there, although we might be on the wrong side. We might be facing away from Saturn. Sometimes, you'd see it go through a whole series of phases. It would remain in the same position in the sky, and we would see the rings going up to 120 degrees from one end to the other. It would be quite a sight there. The Sun would not be as bright as here, but magnitude -22, considerably brighter than our full moon. It would go through a cycle every 16 hours, 2 hours of which it would spend behind Saturn. The other planets wouldn't be that easy to see, mostly because, well, they'd be close to the Sun. The Earth would only be 6 degrees away from the Sun. Jupiter would get to 30, Uranus, Neptune, Pluto, effectively the same kind of thing that we have here. Curiously enough, many of the other moons of Saturn would be about the same brightness as each other. Many of them about as bright as we see Saturn. That was quite an interesting there. But what would we see of Janus? Well, for 12 months, we would see nothing at all. Janus would be behind Saturn. But then it would emerge, magnitude 4.8, so, a naked eye challenge, and it would take 10 months to get to the end of the rings. 4 months to get 75 degrees from Saturn, and 4 months later it would reach quadrature. It would only be about 10,000 miles away, so we'd actually see it rising to about magnitude 1, the same as many of the other moons. And it would appear to be, well, not too different in the size that we see our moon, but of course it would be considerably fainter. That would be the time of an interaction. You wouldn't actually see a great deal of the interaction if you were on one of those moons, but you'd then get the same kind of thing in reverse, and then happening from the other side. But the chairman was motioning to me about time a minute or two back, and I'm aware that since the beginning of the talk, Janus and Epimetheus have moved about 25 degrees along their orbits. They interacted earlier this month, so Epimetheus is only about 2 degrees ahead, but since the beginning of the talk, it has pulled a vital 0.01 degrees ahead, in addition to the around 2 degrees. So, even on the time scale of the talk, this is what has happened. Thank you.
Back on. That's fascinating stuff. That's quite an extraordinary system of moons. Certainly the whole Saturn system is just full of amazing surprises. So, has there anyone got questions for Colin?
Yeah, I was going to raise a question, but I think you kind of answered it towards the end. I was going to consider the fact that in this interaction, one of the main factors, of course, is the fact that the masses of these two objects are very different. Which means the balance of potential energy and kinetic energy is going to be different in the interaction.
Yes, so what happens is that yes, Epimetheus moves in and out by more than Janus does, but approximately proportional to their masses there. Yes, so in the same way, yes, Epimetheus has the bigger horseshoe, it also has the wider horseshoe.
And if they were both the same mass, they're equal mass, what would it be like then? Would it be more of a...
They would, in that particular rotating frame, they'd appear to go almost exactly halfway around, just under, and then back again.
Yeah, interesting.
Any other questions? I think we're all quite amazed by the incredible interactions that we've seen there. That's certainly a fascinating system. So we'll just thank Colin again for taking the time.